Today we're going to do some chaotic scattering stuff. So this is lecture 6. And in the context of chaotic scattering, we're going to do some symbolic dynamics as well, which is very important for things not related to chaotic scattering. So I should tell you about how this sort of thing came about. So I'll give you a little bit of history. So John Scott Russell in the late 1800s saw a boat stop suddenly in a channel, and because the boat just stopped, so the boat was going and then it stopped, and because it stopped there was a raised mass of water that continued to flow. So John Scott Russell chased after it, and he chased it, and legend has it that he chased it for like 2 miles, and it just kept going. So that's where solitary waves, the idea of solitary waves came about. But in general, solitary waves are not necessarily restricted to water. In general, it's a solution to a special type of PDE. So it's a solution to nonlinear evolutionary PDEs that translate at a constant speed while maintaining its profile. So later on in the 60s, Kruskal and Zbyszko came up with a solitary wave solution to the KdV equation. So basically what happens in their solution is you have two waves. Say you have two waves like this, and both of them are going this way, except this is going to have more speed. So this one has more energy in the x direction. So this is going to overtake this. So then what happens is that they combine. So they combine to be a bigger wave. They combine to have a larger amplitude. But finally, after this one passes this one, they maintain their profiles. So it's as if nothing happened. So that's kind of what happens with these waves. So this is, let's say this is V large and V small. So V large is going to be greater than V small. And then this is where it combines. And then this is where the bigger one passes the small one. So it's as if nothing happened. So this is moving, there's some sort of interaction, and then they come apart. And they're just like before. So their velocity is going to be the same, and their profiles are going to be the same, as was before. So this is what Kruskal and Zbyszko did. And then later on in the 70s, so this was done in the 60s, in the 70s similar things were done for the nonlinear Schrödinger equation and the Sine-Gordon equation. So let me tell you what the KdV equation is first, and then write down the nonlinear Schrödinger and Sine-Gordon equations. So KdV, so this is Korteweg-de Vries equation. I don't know how to spell either of the names, so I'm just going to call it KdV. So I know, all right, de Vries is easy. De Vries is D-E and then V-R-I-E, I think. Double E? No, it's I-E, right? Yeah.
Korteweg.
Or I-E-S. I-E-S, yeah. So Korteweg, I don't know how to spell.
KdV is good.
Yeah, KdV is fine. So this is the KdV equation. So this is ut plus 6ux plus uxxx equals 0. So that's Korteweg-de Vries. So this is the PDE where these solutions come from. And I'll tell you what the nonlinear Schrödinger equation is as well. So I'm going to call this NLS. So nonlinear Schrödinger is IUT. And you don't have to write any of this down, by the way. We're not going to study these equations. So this is IUT plus UXX plus the modulus of U squared, U equals 0. And the sine Gordon equation is T UT minus X UX plus sine U equals 0. So these are sort of equations where these types of solutions come from. And then in the 80s, they looked at phi-4 equations. So mathematicians looked at something called a phi-4 equation. So this is what the phi-4 equation is. Phi tt minus phi xx plus phi minus phi q equals 0. So it's like that. So this doesn't have any sort of physical, this doesn't model anything physical. It's just a very interesting mathematical equation. So this phi-4 equation produces waves that are called kink and anti-kink. So basically the waves come together, and it's actually one wave is going to have amplitude A, let's say, and the other one is going to have amplitude negative A. And then they come together, so amplitude is changing in time, and the center, the position of the center, is also changing in time. So they come together, and sometimes they'll go apart, or they'll come together and then they'll bounce back and then go apart, or sometimes they'll come together and then bounce n times, let's say, and then they'll go off. Sometimes they'll come together and then just bounce forever. And yeah, so these are the sort of solutions that you can have. So they call this the n-bounce problem. And this is kind of where chaotic scattering was dubbed. So it's called chaotic scattering because, so if we have x, e, and a, so I'll draw what this sort of thing looks like. So this is going to be, let's say x is going to be as such. So it's going to start off, let me think about this. So x is going towards 0, so it's going to be like this. So let's say it starts somewhere down the road. It's going to come in and perhaps it'll go to 0 and then go off. Or it can come in, so this is x, or it can come in and actually bounce. So something like this, and then go off. Or it can bounce twice and then go off. So obviously this isn't very accurate, but it's somewhat like that. So they come together and they go off, or they'll come together, start to go off, and then come back, and then go off. So that's the sort of thing that happens, and the energies for that will look something like this. So you'll get an increase in energy when it collides, and then you'll get a decrease when it moves away, and then you get some wiggle, and then if it starts to collide again, then you're going to get an increase, and then you might get another decrease, and then some wiggle, and then if it goes off, then you'll get an increase, but then it'll just stay flat later on. And then a similar sort of thing happens with the amplitude as well. So these are sort of things that can happen with the position and amplitude. And what they noticed was when they plotted V in and V out, the velocity that the waves come in at is, so the velocity of the waves will come in at, say, V in, and then the velocity that they come out will be very sensitively dependent on the incoming velocity. So two nearby, if you start at velocities that are close, then you can get very drastic differences in the velocity that comes out. And also with any sort of velocity that's coming in, you can have different types of trajectories. So you can have different types of solutions. So sometimes you'll have a velocity that has, say, 2 bounces, but then you might increase the velocity a little bit, and then it might have no bounces. So that's why this was dubbed chaotic scattering. But this is all PDE stuff. We're interested in the differential equations. So in recent years, and our own Professor Roy Goodman had a lot of involvement in this work. And also, if you've taken a PDE course, you use a book by Rich Haberman. So he's done a lot of stuff with this as well with Professor Goodman. So this PDE can be reduced using something called collective coordinates method to this ODE. So this is what we want to deal with. This ODE is going to be mx double dot and x's of t plus u prime of x. So these are all big X's, by the way. And I want to color code this. So that's why I started off writing it in black. So let me write it like this. So there's a reason I want to color coordinate this. So this is M. It also allows me to use all my markers too. So this is M, X double dot. So we're going to keep the X in blue. T plus U prime of X and then we have plus C. I'm going to keep the A in red, F prime of X. So we have that for the first equation. So this is the X equation. This is the equation where it's the position of the center of the waves. So these waves are symmetric, except that one is, so it's symmetric in the X direction. One has a negative amplitude, but it's going to come in in the same position. So all you have to do is measure the position from the center to the center of one wave. And then you have all the information there. And the amplitude is going to look like this, the amplitude equation.
Is there an equal sign in there?
Yeah, that's 0. So the amplitude is going to be as such. So this is A double dot of t plus omega squared A plus C f of x. So this is what we're currently interested in studying for this lecture. So they came up with this using collective coordinates method. I don't know too much about that, but if you want to learn more about that, then you can ask Professor Goodman or Professor Moore. They both are quite good at using this method to reduce PDEs. But now, a few years back, oh, I should tell you what U of x and f of x are as well, before I tell you about the story. Okay, so U of x is going to equal, so this is e to the negative 2x minus e to the negative x. And f of x so this is also going to be exponential. So f of x is e to the negative x. So then for the capstone course that I did when I was an undergrad, Professor Goodman wanted to come up with a mechanical analog for this. So this is, it seems like, so this is 2 second order ODEs. It seems like you could come up with some sort of mechanical analog, right? So this is the motion of, you know, one thing or one direction, and this is the motion of another direction, let's say. So we have 2 equations that look a lot like motion equations, right? Things that give us the motion of a particle. So it seems like you could come up with a mechanical analog. No one had done it before, so he figured we would take a shot at doing that. So here we're going to suppose something before we construct a mechanical analog. So I'm going to write it like this. Okay, so we're going to suppose here that C equals epsilon. So let me put that in here. C equals epsilon, that's small. And then we'll derive what the mechanical analog is.
I guess it sort of looks like it might be a mechanical analog because it's kind of like Newton's law.
Right, yeah. So there, it's very clear that it can represent the motion of some sort of particle. So we're going to think of it like this. So let me go ahead and derive the mechanical analog, and then I'll show you what we get out of it. So basically, let's first think of a ball rolling on a surface. So now it's rolling on my hand, but if we think of the motion of a ball rolling on a surface, then perhaps we can come up with some sort of mechanical analog for it. So if we think of that, so I know you're a physics major. Did you take classical mechanics yet?
Yeah.
Okay, good. So you're gonna help me out then. So if we think of that, right? So a ball rolling on some sort of surface. What can we use to derive the equations of motion for that? So it's a famous name.
Classical mechanics.
Yeah, classical mechanics, yeah. Famous name.
Lagrangian?
Yeah, so we're going to use the Lagrangian, right? So do you remember what the Lagrangian is? It's very easy in terms of energies.
Yeah.
So,
Another lot of X dots.
well, okay, but let's not, so that's when we get to Euler-Lagrange equations, right? But the Lagrangian itself isn't too bad. So it's what? It's what energy minus what energy? You only have 2 options.
Just potential and kinetic.
Right, so what minus what though?
Kinetic minus potential.
Yeah. So T minus U, let's say.
Clear image, right?
So the Lagrangian is the kinetic energy minus the potential energy. So that's what the Lagrangian is. Do you remember what the Euler-Lagrange equations are? Okay, so I never remember these either. So we're going to write them like this. So that's the Lagrangian. Let me just write it down. And the Euler-Lagrange equations are as such. So this is Euler-Lagrange equations. And they're going to be partial L partial x equals d dt partial L partial x dot. And then the equation for the other variable is the same thing except in that variable. So it's going to be partial L over partial y equals d dt partial L partial y dot, and etc. So if you have more dimensions, then it's going to be similar to that. But now if we're thinking of a ball rolling on a surface, then what happens with, say, the H, or say the Z direction? So let's think of a surface so we're thinking of a surface in 3 dimensions. So a surface embedded in 3 dimensions. So how many dimensions do we have there? So how many dimensions is on the surface of my hand?
How many dimensions?
2, right? So we're going to take this 2-dimensional thing, but it's going to be folded in some sort of way, right? So we're going to have a Z direction in there because it's moving in the Z, but how can we represent the Z as a function? So we're going to we're going to think of a ball rolling on the surface where the surface is represented by Z equals H of X and Y. So as we're moving on X and Y, the Z is going to change, so that's why it's Z equals H of X and Y. So we're going to write things in terms of Z, but then we're going to substitute in this H of X and Y. And this H of X and Y is the surface that we want to find. So we're going to try to figure out what this H of X and Y is. Now we have to figure out what. So what else do we need here? So what is T and U? What are T and U? So let's do the easy part first. How about the potential energy? What is the potential energy? So this is potential energy. So this is U equals what?
Usually it's like MGH.
Yep, so that's it. So mgh of X and Y, right? So that's just mgh. And then we need the kinetic energy. So that's the kinetic energy of a ball rolling on a surface. I don't remember these things either, so I'll just give you what that is. But we should remember that it's just going to be 1/2 mv squared plus, and then do we remember what the other? Yeah. So what is that?
I don't remember.
1/2. What's the rolling analog of m? No. What's the analog of mass for a rolling body?
Moment of inertia.
Yeah, so moment of inertia. So I, and then what's the analog of velocity? Well, it's just another type of velocity.
Like omega?
Yeah, so omega, so angular velocity, right? So this is really just going to be 1/2 mv squared plus 1/2 I omega squared, right? Although that might be capital omega, I forget how it's written, but that doesn't matter too much. But this is the way it's set up, right? Where this is going to be the angular velocity, and this is the moment of inertia. So this is going to be 7/5 times m over 2, so 1/2 m, times x dot squared plus y dot squared plus hx, so this is the x derivative of h times x dot plus the y derivative of h times y dot squared. So we get that. So this is basically just 1/2. We're pulling out the 1/2s. We have the mass. We have the mass in our moment of inertia as well. So that's where we get the 7/5 from. And then we have our x dot squared plus y dot squared plus, and then this is going to be z dot squared. So this is just v squared. So then we have everything. So we have our t. So I can't put this down just yet. I have to skip some steps here. So now we have our t, and we have our u, so we have our Lagrangian. So let me write down the Lagrangian, and then I'm going to give you a small assignment. So this Lagrangian is going to be 7 over 5 m over 2 times x dot squared plus y dot squared plus hx x dot plus hy y dot squared, and then minus mgh of x and y. So now what we want to do is take this and plug it into the Euler-Lagrange equations, but instead of doing that on the board, I'm going to let you guys do that for homework. So take the Lagrangian and just do the operations. So do the operations on the Euler-Lagrange equations, and then you're going to isolate your two differential equations. So it's basically just a matter of doing the calculations, and you can do the calculations on Mathematica or Wolfram Alpha. I don't really want you guys to do it by hand, but just make sure you know how to do these calculations. So then after that, we're going to get, also we're going to assume that h varies slowly, so when you do these calculations, h is going to vary slowly, so what do you think that means?
Like dH/dt would be 0? Is that what
Not, well, so dH dt is going to be small, but now h, say, well, not necessarily dH dt, but I guess we can think of it as that, but say hx, right? So dH dx squared, that's going to be even smaller. So we can kind of neglect it. dH dy squared, we can kind of neglect that. dH dy times dH dx, we can kind of neglect that. So we can neglect the higher order terms, basically. So when you do these calculations, then you can just neglect the higher order terms, and that'll make your life a lot easier. And then we're going to get the approximation that we have here. So then this is going to approximately give us this. So let's see. I'm going to erase this part then. So you guys have this down, right? Okay.
Let me ask the physicist a question. Do you know how do you get the Euler-Lagrange equations from L? Recall the basic idea? Something with Hamilton, something or other? Does that ring a bell? Hamilton's principle? You take the first variation of the action and you set it equal to 0, and that's how you get the Euler-Lagrange.
So here, in order to convert this into our rolling ball system, we're going to let x, so small x equal big X, and y equal a. So we're going to let that in order to convert it. So then our equations become, so we're going to approximate this as such. So this is obviously not an exact replica, but it's close enough. Times h of x and y So it's going to be close enough to the dynamics of that. And for y, we have y double dot plus 5 over 7 gh of x and y. So we're going to get that. So now we have our equations, but what do we need? What else do we need? So we have the equations of motion. But now we want to replicate this. So how are we going to do that? So this is approximately the equations of motion for a ball on a surface that doesn't have very large slopes. And we want to figure out what that surface is to replicate this, right? So how are we going to do that? Do you see any similarities here? So we're okay with the x double dot. We can kind of ignore the m. We can assume it's non-dimensionalized. And then we're okay with the y double dot, right? But then we have plus some terms. Well, this is just a function of x and y, x and a, and this is just a function of x and a as well, right? And then we know what f and u are. So we can write it like this. So h of x and y is going to equal 7 over 5 g times u of x plus omega squared over 2y squared plus epsilon f of x times y. And we get that just from matching this up with our equation before. So we're going to have that for our h. So that basically gives us our surface. So that is going to be this thing. So that's basically this. So that's h. And here, x is in this direction. So this is x. That's the x direction, and then this is the y direction. So that's basically our h. And the motion of the ball on this is going to replicate the dynamics of this. So basically what we want to do is reproduce that v in, v out curve or data that I mentioned earlier. And this is going to kind of reproduce the v in, v out that we get here. So when we see the v in, v out for the ball on the surface, it will be qualitatively similar to this, to the v in, v out of these waves. So that's the idea of that. So now we need to figure out how to get v though, right? So that's what we're concerned about. We want to calculate v in and v out. So it's important to figure out how to get v in, right? So how do we do that? Let's say if we're using this ramp. So do you know what shape that is? I can never pronounce that, but do you remember from calc? How about if I turn upside down? What about a wheel? Say you put a point on a wheel and you watch that move.
I think we talked about this.
Yeah, it's a brachista something. I can never pronounce it, but it starts with a B and it ends with a stone, or no,
Cone.
or a cone. Yeah. So it's going to be that thing, the thing you learn about in calc. So we want to know what the v in is. So here the initial conditions are going to be this. So if it's coming off this ramp, so let's pretend that this ball is coming off the ramp and then entering this system, I guess, this surface, and it's going to come off with no variation in y, and the derivative in y is going to be 0 as well, right? Because it's coming off straight into the x direction. So here, y of 0 is going to equal 0, and y dot of 0 is also going to be equal 0. But now we want to figure out x. So we're going to say x is starting at 0, So x of 0 is 0. So the only non-trivial initial condition we have is x dot of 0. But how do we figure out x dot of 0? What are we going to use here? So the ball is starting at some position, right? How are we going to figure out what v is at the end?
You use conservation of energy.
Okay, good. So applied math,
Neglecting the friction.
right, exactly, yeah. So I could get you guys to deal with the friction, but that's going to make things more difficult, and I don't want to do that yet. So if you want to see how we deal with the friction, I can send you the paper Professor Goodman and I wrote on this, and then you can see how we dealt with the friction. But don't worry about the friction for this, for your homeworks. So if we neglect the friction, then we can just use conservation of energy, and that's basically, like, I don't know, 80% of the time, that's what we're doing. We're using conservation ideas to derive equations in applied math. So we're using a lot of conservation, a lot of Newton's laws, things like that. So we're going to use conservation of energy, so how are we going to do that?
Well, you would have that yeah, you would set for that system that the potential energy at the bottom would be 0. And
Okay.
you have whatever the ball is starting at, that would be equal to mgh.
Okay,
And
so
then that would equal 1/2 mv squared.
we're going to have this, right?
Solve for b.
So we need the rotational kinetic energy as well. So that's going to give us 7/5 m over 2 times 1 plus hx squared, and then times v squared. So that's a kinetic energy at the bottom, right? That's considering rotational and translational kinetic energy. So that's a kinetic energy, and then the right-hand side is easy, right? So what's the right-hand side? What's the potential energy then?
mgh.
So mgh, right? But this is mgh of x, because we don't have any variation in the y direction. So that's why this simplified a lot from the t we had before. So since we have this, now we can calculate what this is going to be. But do we remember what I said about the change in h?
Very small.
So it's small, right? So that we can approximate as 0. So if we approximate that as 0, we're going to get this. So this is going to be, and let's cross out the m's first. So this is going to be 7/10 v squared equals, or approximately equals, gh of x. So we're going to have that, and then that means that v squared, so v is going to be approximately, so this is 10/7, so it's going to be radical 10/7 gh of x. So in order to figure out what Vn is going to be, all we're going to do is measure how high we're starting our ball from. So that's all we need to figure out Vn. So that's basically what we're going to do. So I forgot to bring a tape measure, but we have some rulers in the little lab that we can use. So that's what you guys are going to do today. We're going to start off the ball at different Vn's and try to get as many possible solutions or trajectories as we can. So we can only get 4 possible trajectories on this because of what? So I said before that this was chaotic, right? We can get any sort of trajectory. We can get things that or collide and then go away. We can get things that bounce once and then go off. We can get things that bounce n times. We can get things that bounce forever. So why can't we do that here, though? What's the one thing we talked about that makes things difficult. Yeah, friction, right? So that's why we can only have 4 types of trajectories here. But we'll see that when we do the experiment.
Wait, why isn't x sub h squared approximately 0?
Oh, we're just saying that we want a surface where the slopes are never too large.
Okay.
That's why. So it's just an assumption of the surface, but we created the surface to behave like that, or for the ball to behave like that on the surface. So that's the experiment we're going to be doing today, but let me briefly talk about symbolic dynamics. So I want to talk about symbolic dynamics because of this thing. So this is a chaotic scattering system as well. So basically light is going to enter, and then something's going to happen, light's going to exit, and depending on how the light enters, the exit, the type of solution we get when the light exits is going to be very different. So if we make a small change in how the light enters, we're going to make a large change in how the light exits. So that's why you get a fractal-like structure if you shoot light into this. And if you look at it, you can kind of see the fractal-like structure here. Obviously, it's not the ideal situation, I guess, with the lighting and everything. So if you did it properly, you'd really see it. But if you even here, if you look at it, you can see a fractal structure there. So that is going to lead us into symbolic dynamics because the ball can enter, and then either it goes. So if you can kind of see it, there's 3 here, and then there's 1 on top. So it enters. Either it can hit this, this, or this, and then escape. And that's going to be sensitively dependent on how the ball is entering. So basically the ball is going to always hit this ball, hit this, or not the ball, the light is going to always hit this ball first, this sphere first, and then it's going to travel to any of the other spheres, and depending on how it's changed slightly, that's going to make a big difference on where it travels. So then it's going to hit this sphere first, and then it could hit, say, this, and then it could hit this. So we only have 3 possible ways the ball can move, right? So either it's going to move in this direction, or in this direction if it hits this sphere. Now, if we look at the light coming from this sphere, same sort of thing. It can either move in this direction, or it can move in this direction or that direction, right? So you only have 3 choices of where the light can go. So that's the idea of symbolic dynamics. You take this very complicated system, but then you boil it down into 3 possibilities. But then what makes it complicated is how you're going to change between these possibilities, right? So you can get a string of possibilities, but you can get a string of almost any sort of possibility, right? So anything that's possible will happen. That's the basic idea. So you get only a few different possibilities, but everything can happen. So that's the idea of using symbolic dynamics. You're taking something very complicated, but you're analyzing it in a simple way. So let's look at this very simple system. xn plus 1 equals 2xn mod 1. So I remember when I was taking Professor Blackmore's class, I think it was my junior year, I was taking 473, and this was on the final exam. So I guess he likes that problem. So this is going to look like this. So this is called the bit shift map or the mod 1 map. So this is what it looks like. Let's say we have the unit square. And hopefully I drew it okay. So yeah, that's unit-ish. So let's say we have that. And let's draw in. So yeah, let's go ahead and draw this in. So I'm going to draw y equals x in there. So this is 1, 1. This is obviously 0. And this is going to be xn plus 1. And this is xn. So let's draw in y equals x. And then let me see what colors I want to use. So yeah, let me use blue for this. So does anyone see what it's going to look like? So do we know what mod 1 means? So mod 1 basically means that if, let me give you an example. So let's say 1.2 mod 1. That would be 0.2. So that's the idea, right? Or 1.5 mod 1, that would be 0.5. So mod 1 is just looking at it from 0 to 1, so you're just kind of re-normalizing, I guess. So that's the idea of mod 1. It kind of resets it into the 0, 1 domain. So then this is going to look like this. So it's 2xn mod 1. So that means things that are here, it's going to reset. So anything here is going to look like things here, right? So this is going to be the line 1/2. So this is going to be the point 1/2. So our system is going to look like this. So hopefully I have this correctly. Let's put that here. So our system is going to look like that. So since we have this over here, we're going to have the same thing over here. So that's the basic idea. So that's why it's mod 1. So if we get something here, it's just that point is going to be the same as something over here, right? So if we have an initial point here, then it's just like if we had an initial point here. So that's mod 1. And now we can draw the cobweb plot. So let's draw the cobweb plot, see what sort of things are possible first, and then we'll go and do the analysis. So let's take an initial condition here. So what are the possibilities for that initial point? Where can it go? So let's go ahead and go forward with the cobweb plot. So it's the next xn is going to be here, right? So where is that xn going to go? Up. So that's going to go up, right? To this. So it's going to go to that point. And then that's going to go like this. So where is that going to go?
Back down.
So it's going to go back down. It's going to go here. And then let me just move it forward until we get something interesting. So we move it here. Okay. Yes, okay, good. So this is going to go up to this point. But now, where is that point going to end up going?
Oh, back up.
So it's going to go back up, right? Over here. So we can kind of see all the possibilities here. Either it can stay where it was before, or it can shift to the other part, right? So here, it just stayed in this interval, right? It just stayed on this line. But all the iterates before were kind of bouncing back and forth between the two lines. So there are only two possibilities, right? So an iterate can only end up in its own line, or it can bounce to the other line. So there are only two possibilities for the orbits of this map. So that's what we want to kind of analyze. So let's call this I0, and let's call this I1. So the only possibility is that if you're on I0, you can stay on I0 or bounce to I1. If you're on I1, you can stay on I1 or bounce to I0. So that's the idea. So now, so we're going to note that xn is between 0 and 1 always. So xn is between 0 and 1. So we have a very natural way, so since this is mod 1, we have a very natural way we can represent xn. So how do we think we're going to do that? What does this remind you of, this two possibility thing? Think of twos. You can either have something that's this or something that's that. Let's say I make a statement, some sort of statement. There's only two possibilities for that statement, right? Either it's false or it's true. So what are we going to represent xn as?
Binary?
So we're going to use binary, right? So we can represent xn in terms of binary numbers. So let's see how I write this. So let xn be binary. So let's take this example then. So we're going to say let xn be binary. And let's take this example. So we're going to have alpha k equals 0 or 1. Then we can say that, so any xn is going to be this. Any xn is going to be represented as 0 dot alpha naught, alpha 1, dot 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 alpha k, dot dot dot, right? So it kind of continues, since it's between 0 and 1. So we can represent any xn like this, with this string of digits, of binary digits. But let me ask you this. What happens at 1? Why do I have a 0 here and then a decimal and then digits going on? What happens at that 1?
It stays at 1.
It's 0.
It stays at 1, yes. But like how would we represent this here?
It's 0.
No.
K goes to infinity.
What happens as k goes to infinity? So let's think of this. What is 0.99999, etc.? What does that equal?
1.
That equals 1, right? Well, we have the same sort of thing here, right? 1, 1, 1, 1, 1, 1, etc. So that's going to represent 1. So that's why we don't need a digit here, right? We don't need a digit here because we have a different representation for 1. So 0.9 going on forever is just a different representation of the number 1, but it's the same number, right? So that's why we keep it as 0 here and then decimal and then etc. So xn is going to be like this. But now let's find xn plus 1. So xn plus 1 is going to be 2xn mod 1. So what happens when we multiply xn by 2? So do we know how it works in binary?
It's going to either be 0, in the 0, 1 phase. Something about.
So this is going to be 2 to the 1, right?
2 to the 1.
So this is really, okay, let's write it in binary.
It's like-
I should have written this in binary. So 1, 0 times xn. So 1, 0 in binary, but that's just 2, times xn mod 1. So then what is it? What happens if we do 10 times a decimal number? What happens to that decimal?
Just moves it.
Yeah,
over
so
space.
same thing in binary, right? So 1, 0 times this decimal is just going to shift everything over to the left. So this is going to be alpha 0, decimal, alpha 1, alpha 2, dot, 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 alpha k, dot, dot, dot. So we get this, but we have the mod 1. So now we're at a number that's like 1 point something, right? But what do we know that mod 1 does?
Cuts off the 1.
Okay, so it's going to cut
Cuts off
this
the
off,
alpha
right?
0, yeah.
So this is, it doesn't have to be 1 point something. It could be 0 point something, right? But if it's 0 point something, then we just get this. If it's 1 point something, then it's going to reset it, right? So then we're going to get that this is 0 point alpha 1, alpha 2, dot, 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 alpha k, dot, 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 right? So we can represent this, this fairly complicated thing, and this can be chaotic actually. But we can represent this just by symbols, right? We can represent it in binary, we can represent it in terms of symbolic dynamics. So the idea here is that we can get any string of numbers. So we might have, we can have an initial condition where we keep applying this map and we get all sorts of possibilities. So that's the idea of symbolic dynamics. So this is a very simple example. Obviously this is a more complicated example. But over here and over there, we're going to get the same type of dynamics. So that's why symbolic dynamics are important in scattering theory and chaotic scattering. So that's basically all I wanted to say about chaotic scattering. So unless we have any questions, we can go to the experiment.
Just a point. This map, for fairly obvious reasons, is called a shift map because it just shifts the representation by moving the decimal point, or a binary point in this case, one place to the right. It turns out that this kind of chaotic behavior is typical of a whole class of chaotic dynamics that you could represent them in terms of shift maps. For example, the snail horseshoe, which I'll talk about one of these days, can also be represented as a shift map, but in that case a double shift map.
So Professor Blackmore might even talk about it next week, actually. Might. I don't know if you want to do that with Loren's stuff. Because I'm going to the conference this week.
Okay, I guess I could.
If you want, I mean.
No. Okay.
So, yeah, I'll be at a conference, so I figured Professor Blackmore, it would be good if Professor Blackmore does it on Tuesday. Plus, he's the expert here. Okay, so that's different types of chaotic scattering that we can get. So I guess we can do the experiments. Is there anything else I wanted to say?
One more thing about this. Sorry, but what this says is that in terms of the dynamics, the full dynamics of this one-dimensional map, you can represent them. They're equivalent to this shift map. And because of that, if you look at the way the shift map works, that'll give you dynamics, it tells you pretty much everything about the possibilities. For example, you could show that you have periodic solutions of all periods. Think about that. Periods, you have to apply it, you have to move decimal n places to the right, and you want to repeat it. That would represent a 10 cycle, let's say, or an n cycle. It also, and I'll talk about that next time. From this you can also prove that this thing has dense periodic orbits. It has dense orbits because the dynamics reduces to the symbolic version, which is a lot easier to analyze than kind of the geometric, even the cobweb version of the description here. So they're good things to have if you have it.
So these seemingly simple maps are very useful. So we actually use this to prove that one of our systems was going to have chaos if we perturb it in a certain way. So we use exactly this idea. So it's very useful. So yeah, if there are no more questions, then we could just do some experiments then.